Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk a little bit more about gamma distributions. Well, to be more precise, we will talk about another particular case of gamma distributions. We will talk about chi-square distributions. But before we talk about chi-square distributions, let me remind you that we have said that the gamma distribution family has a few interesting particular cases, such as the exponential distribution, which we have talked about in another video. Remember that when alpha equals 1, then gamma distributions turn into exponential distributions. So exponential distributions are particular cases of gamma distributions. Make sense? Okay. So another member of the gamma distribution family is the chi-square distributions. I think we have that here, but we will go back to this expression, okay, in a few minutes. So let me show you how chi-square distributions are defined. So in that case, in the case of chi-square, instead of making the value of the parameter alpha constant, what you do is you make beta equal to 2, and then alpha is such that you can, well, it has to satisfy this restriction. Alpha must be a number v, or nu for the degrees of freedom, the degrees of freedom divided by 2, right? And instead of using alpha for the parameter for chi-square distributions, this is just notation, right? We use that nu, a Greek letter, for the degrees of freedom. Some other authors use n for the degrees of freedom. It doesn't matter, as long as you understand that that's the parameter that defines a chi-square distribution. And deep down is just the alpha parameter of a gamma distribution, but it must have this kind of form. Okay? Okay. So let's talk about an example. So you can see that it is not that hard to deal with chi-square distributions once you have dealt with gamma distributions. Okay? So let's try and do this exercise together. Okay, so we have an expression for a PDF. So k is a constant, at this point is unknown to us. So the PDF up to that constant is y cubed e to the negative y divided by 2. Okay, so now what we would like to do is answering those questions. First, we want to find the k, the constant that makes that expression a legit PDF, a legit probability density function. Then they are telling us that they believe that this is a chi-square distribution. So since the parameter that defines a chi-square distribution is that nu parameter, okay, we want to find it. And once we have it, well, we would like to find the mean, the expected value, and the standard deviation of the random variable y. Okay, so let's try and do A first. Let's try and find the value k that makes that density, well, that expression a legit probability density function. Okay, so take a look at that. So it's y cubed e to the negative y divided by 2. Okay, so let me write that down here. Let me open a new one here. So we have f at y equals k y cube e to the negative y divided by 2. Okay, and that's for y's that live here between 0 and infinity. Okay, we know that it's going to be 0 elsewhere. Okay, so take a look at this guy. Now let me go back to our lecture notes, to the slide where we have the expression of a gamma distribution. So we have this part, right? Y to the something minus 1 e to the negative y divided by beta. So beta seems to be fine, right? So beta seems to be 2, and we know that that's a restriction that chi-square distribution must satisfy, that beta must be equal to 2. Okay, now we have that 3 here. Note that 3 is the same as 4 minus 1, and we're going to be doing that because we want something that looks like this: y to the alpha minus something. Well, y to the something minus 1, right? So let me write that 3 as a 4 minus 1, right? So from that, it seems that we're dealing with this, right? Alpha equals 4, beta equals 2. But if that's the case, that k that we need there in order to have a legit probability density function must have this form: 1 over beta to the alpha times gamma evaluated at alpha, gamma the gamma function. Okay, so 1 over beta to the alpha times gamma function evaluated at alpha. Let's write that down. 1 over beta to the alpha power gamma function evaluated at alpha. So let's evaluate. So it would be 2 to the power 4 gamma evaluated at 4. Right? So now let's do a little bit of math, right? So that would be 2 to the power of 4, so that's 2 times 2, 4 times 2, 8 times 2, 16, right? And then we know that the property that we showed about gamma functions is that gamma at an integer n equals n minus 1 factorial, so it would be 3 factorial, and 3 factorial is just 3 times 2 times 1, so that's just 6, right? So let me write that down here. One over 16 times 6, but that's just 1 over 96, right? So we have found that constant k that would make that expression a legit probability density function. And again, I wanted you to see that chi-square distributions are just particular cases of gammas. Now let's go back to the problem. I think that we also wanted to do something else. right? So we have found K. Let's find B, the degrees of freedom. So remember that this is A. So remember that alpha must satisfy a relationship, right? Alpha in general is going to be nu, the degrees of freedom, divided by 2, right? So nu must be here, yeah, divided by 2, which means that if we solve for nu, what we end up with is nu equals 2 times alpha, right? So in this case, it would be 2 times 4, that's 8. So that means that we have a chi-square distribution with 8 degrees of freedom, okay? And then finally, the mean and the standard deviation of y. So remember that we showed that the mean and the variance of a gamma distribution are given by these formulas, right? So we can use them to find the expected value of a chi-square. It's just a particular case, right? So it would be just for part C, the expected value alpha times beta so it would be 2 times 4, 8, done. Note that the expected value of chi-square distribution coincides with the degrees of freedom. And then the variance, let's use that formula that we have for the variance of gamma distribution. We have it here, alpha times beta squared. So alpha times beta squared so it would be just alpha is 8, alpha is 4 times 2 squared. So 4 times 2, 16, right? And if you want the square root, you know that the standard deviation is the square root of the variance. So square root of this guy just 4, right? That would be the standard deviation. Okay, that's it. We're done. So let's summarize what we did together, right? And let me go back to the problem that we solved. So what we did here in this video was we talked about another important particular case of gamma distributions. We talked about chi-square distributions. What we saw is that in this case, right, what you want to do is set beta equal to 2, and then alpha must satisfy a relationship. Alpha must have a particular form. It must be a number, nu, divided by 2, and that nu number is it's just a Greek n anyway. That nu represents the number of degrees of freedom for the chi-square distribution. That's the parameter for a chi-square distribution. But if you want to find, for instance, expected values or variances for those guys, you can rely on the formulas that we have for the general case. right? That's what we saw. And something that we also saw is that it is useful to be able to identify the form up to a constant of a PDF, because that allows you, for instance, to find like in the first part of this problem, that allows you to find the right constant, the constant that will make that function a legit PDF. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.